Welcome back to the Deep Dive. We've got a fascinating set of sources in front of us today, some academic research, a really specific technical study, and even some real-world opinion straight from a Reddit thread.
Yeah, it's a great mix. Let's just look at the theory, but also the practical side, how these things actually play out.
Absolutely. And our mission today is to take all this stuff and really zero in on one of the most, well, critical ideas in blockchain,
Yeah.
consensus algorithms.
Right.
Basically, how do all these different computers, these nodes in a network, agree on what's true? What's the single correct version of the ledger?
Yeah, without that agreement, the whole thing kind of falls apart. You don't have a reliable record. Consensus is it's what lets you trust the system itself instead of needing like a bank in the middle.
Exactly. So let's dive into these sources. We're going to unpack what consensus really means, look at the different ways networks try to get there, dig into the trade-offs,
Yeah,
because there are always trade-offs.
always.
And maybe highlight some of the newer ideas being researched. The goal for you listening to walk away with a solid grasp of this really core piece of blockchain tech.
Sounds good.
All right, let's start simple then. Based on the sources, what is a blockchain at its heart?
Well, the sources describe it as basically a shared digital ledger,
Yeah.
but it's distributed, decentralized. So think of a database that isn't just in one place, but copied across loads of computers in a network.
Okay, distributed.
Okay.
And it gets the name blockchain because of how the info is linked up, yeah?
Yeah.
Data gets put into blocks.
Right.
And each block has its own sort of digital fingerprint, its hash, and crucially, the hash of the block that came right before it.
Exactly. And that chain of hashes, that's the key to the security. If someone tried to, say, change an old transaction, they'd alter the data in that old block, but that changes the block's hash, and the next block is pointing to the original hash, so you break the link.
Ah, okay.
To make it work, you'd have to recalculate the hash for that block, and then the next one and the one after that, all the way down the chain.
Which, yeah, across a big network.
Yeah.
One source just calls it very impossible to pull off without anyone noticing.
It's that cryptographic linking. It's incredibly powerful. And, Bitcoin kicked this off in 2008 for money.
Right, Satoshi.
Yeah. But the sources mention this blockchain 2.0 idea, taking it way beyond just currency.
Plus, it's not just one type, right? The sources talk about public ones, totally open, private ones that are restricted, and hybrids that mix things up.
But for all of them, you need consensus. That's the process, the set of rules the network follows for all the nodes to agree on the right order of transactions, the valid blocks to add to that shared ledger.
So it's the engine that lets these things run without a central boss. Instead of a bank saying yes or no, you have participants, miners or validators,
Depending on the system, yeah.
doing the verifying and agreeing based on the rules.
Exactly. They're like the distributed judges of what's true for that ledger.
And your sources make a point that there are lots of different ways to achieve this consensus. It's not just like one or two methods.
Oh, yeah. The variety is huge because, and we'll definitely get into this, every single method comes with its own set of, compromises. The consensus mechanism really defines the whole network's personality, you could say.
Okay, let's get into some of the big ones mentioned in the sources then, starting with the classic, proof of work, PoW.
Right, PoW. Fundamentally, it's about spending energy, computational energy. The participants, miners, they use powerful computers to solve these really tough math puzzles. It's like a global race.
Correct.
Yeah, the first one to find the right answer gets to propose the next block of transactions. They broadcast it, others check their work, and if it's valid, boom, it gets added to the chain.
And it's kind of funny, the idea is actually from '93, right? For stopping certain web attacks. Then Bitcoin made it famous in '09. The work is literally the computer churning away, finding this random number, a nonce.
Exactly. That nonce is the key. Combine it with the block data, hash it, and if the result meets a specific target, you've found it.
And the payoff for all that work, security. The sources say PoW offers very high security in some methods, like Hashcash. And it's decentralized by design, because in theory, anyone can mine. Controlling most of the network's power for a 51% attack is supposed to be super hard, super expensive.
But that expensive part, that's the massive downside everyone talks about, the energy use. It needs so much computing power, high electricity costs.
Yeah.
The sources also mention significant delay, high latency, blocks aren't instant, And scalability. The base version is rated low. It struggles with lots of transactions per second.
And compatibility with, like, small Internet of Things devices. Very low, according to one source, though they mentioned some miner twins idea. Plus, you have mining pools.
Right, where miners team up. That actually brings back a bit of centralization risk, doesn't it? Big pools could theoretically get together.
Not ideal. So to tackle those energy and speed problems, we got proof of stake, PoS.
PS flips the script. Instead of raw computing power, nodes get chosen to validate blocks based on how much cryptocurrency they own and are willing to lock up or stake as collateral, like putting down a security deposit.
And that's where the huge energy saving comes from. No crazy math puzzles means.
It's much higher energy efficiency, yeah. Compared to PoW, it's night and day.
Wow.
It also helps with high scalability, especially using techniques like sharding, basically splitting the network load to process things in parallel. One source mentions it's better than PoW for things like Internet of Vehicles. And security against double spending. One source rates it higher than PoW.
And Ethereum switching to PoS is the massive real-world test case, right?
Yeah.
Aiming for what, a 99.95% energy cut? That's enormous.
It really is. But, POS has its own wrinkles. The sources say it can be somewhat centralized. Why? Because validators with more stake have more influence. Simple as that.
Makes sense. Rich get richer, kind of.
Potentially, yeah. It also has different issues with pool mining than PoW does. And you mentioned sharding for scalability. Well, that can open the door to shard takeover attacks if it's not designed carefully.
Okay, so still trade-offs. And that centralization thing seems even more pronounced in the variation called Delegated Proof of Stake, DPoS.
Yeah, DPoS adds another layer. Instead of everyone with state potentially validating, token holders vote for a small, fixed number of delegates or witnesses. These elected folks are the ones who actually validate transactions and make the blocks.
Like electing representatives.
Exactly. And that system has speed benefits. Sources list low latency because there's no puzzle solving, and block creation is streamlined with that small group. Also high energy efficiency, like PoS.
Right.
And because it's a smaller group validating, you get enhanced scalability and faster transactions. It can handle more volume than PoW. Plus, it's accessible. Anyone with tokens can vote, which is easier than setting up a PoW mining farm. And there's this idea of democratic governance and accountability. Well, delegates want to stay elected, right? So they're incentivized to act honestly. And the system plans for penalties, like slashing, if they misbehave.
But the flip side seems pretty obvious, and the sources state it clearly. Centralization. It's rather centralized because power rests with those few elected delegates.
Right.
A direct trade-off between efficiency and decentralization.
Textbook example of the trilemma in action.
And speaking of centralization, proof of authority, PoA, seems to really lean into it.
It does. PoA uses a set of pre-approved, known validators. These aren't random people. Their identities are verified. They're essentially trusted system moderators given the power to create blocks.
Okay, so trust is based on reputation, not stake or work. What are the pros?
High security, apparently. One source even says safer than PoS. And it's got better Byzantine Fault Tolerance built in than, say, a simple centralized database, even though it is permissioned. Performance-wise, higher than PoW, energy efficiency and throughput because it's managed. Scalability also higher than PoW. And there's a variant, HDPoA, Hierarchical Distributed Proof of Authority, that's specifically noted as validated for low-power IoT devices.
But the big caveat, just by definition, it's centralized.
Yeah.
Validation is limited to that approved list.
Yep, that's the deal.
Okay, moving on to something different. Proof of history. PH. Solana uses this, right?
That's the famous example, yeah. POH is interesting because it's not strictly a consensus mechanism itself, but rather a way to create a verifiable order of events before consensus happens. It uses a kind of cryptographic clock.
A clock.
Yeah, basically a function that outputs a sequence of hashes super fast, like millions per second. This creates a time-stamped historical record that everyone can agree on.
And that speed is the key benefit.
Exactly. That clock leads to POH's main claim, high throughput. Sources say it's great for things needing really fast transactions gaming, maybe high-frequency trading. One table also lists it's high on energy efficiency, security, and scalability. Decentralization is sort of tied to validators just needing to provide a valid signature.
What are the downsides then?
Well, it really depends on that cryptographic clock. If that could somehow be messed with, it's a big security risk. It also needs high level of collaboration between validators. And one source notes it has probabilistic finality.
Ah, okay, you mentioned that before. Probabilistic finality versus deterministic. Can you quickly recap the difference for, someone actually using it?
Sure, deterministic finality means once your transaction is in a confirmed block, it's 100% done, mathematically irreversible. Final. Probabilistic finality means it gets more and more final as more blocks get added after yours. The chance of it being reversed gets incredibly tiny very quickly, but it's never absolute zero.
So maybe for a huge transaction, you'd wait a bit longer on a probabilistic chain, just to be extra sure.
Exactly. You wait for more confirmations to increase your confidence level.
Got it. Okay, now let's look at proof of vote, or PoV. This sounds democratic.
Sort of, yeah. It uses a voting system. There are different roles: commissioners who vote and verify, butlers who get randomly chosen from candidates to actually propose blocks they don't waste power, like PoW miners, and then butler candidates and users.
The goal seems to be speed again, high throughput and confirmation time.
That's the aim. Pros listed are higher than PoW energy efficiency, medium scalability faster than PoW block creation. And a source makes a bold claim: the network will never bifurcate, meaning the chain won't split. Plus, it can handle attacks on up to half the key nodes.
What about security overall?
Rated lower than PoW, but within the satisfactory level, so it's a known trade-off. Also not really used in IoT yet, though the potential is seen.
Okay. We also saw Hedera Hashgraph mentioned using a totally different structure, right? Not a chain, but a DAG.
Correct. A directed acyclic graph. Hashgraph combines that DAG structure with something called a gossip protocol. It's described as leaderless, asynchronous, Byzantine Fault Tolerance, ABFT.
Gossip protocol, like nodes telling each other information.
Pretty much. Information spreads really fast, node to node, like digital chatter, and consensus kind of emerges organically from how that information spreads and gets time-stamped within the graph structure.
And the benefits,
Yeah.
the sources sound quite positive.
Yeah, they list low latency because of that rapid gossip, excellent security. The structure itself makes it really hard to secretly change history. One source even calls it extremely decentralized, with nodes chosen by a council, avoiding single points of control. And that comparison table we saw rates it highly across the board: energy, security, scalability, decentralization.
Any listed cons?
Well, like POH, that same table lists its finality as probabilistic. That's maybe the main point of comparison against systems offering deterministic finality.
And underlying a few of these POA, Hashgraph is this concept of Byzantine Fault Tolerance, BFT. What exactly is that?
BFT is a really fundamental property you want in distributed systems. It means the system can keep working correctly, keep reaching agreement, even if some nodes crash. Or worse, even if some nodes are actively malicious and trying to lie or disrupt things. That's the Byzantine part, dealing with potential traitors.
Okay, so it's about robustness against bad actors or failures.
Precisely. And the sources note that to guarantee security in many BFT systems, you usually need a strong majority of nodes, like over 2/3, to be honest and working correctly. Liveliness, the network's ability to keep processing transactions, also depends on how many nodes might be dishonest. In permission systems, things like access control can help manage risks.
Wow. Okay, that's a whirlwind tour of different algorithms. And like you said, each one seems to nail some things but compromise on others. Which brings us squarely back to that core problem the sources keep mentioning, the blockchain trilemma.
The trilemma, yeah, it's the idea that it's incredibly hard, maybe impossible, for a blockchain to simultaneously maximize three key things: decentralization, security, and scalability. You often have to pick two or find a balance that compromises a bit on all three.
The Reddit thread really brought this out. You had some people saying, look, it's basically the law of physics. You can't solve it. There are always trade-offs. But then others were pointing to specific projects saying, no, we're solving it or getting close.
It's the central debate, really. And if you look back at the algorithms we just discussed through that trilemma lens, the trade-offs become super clear.
Okay, let's do that. Security first. PoW is secure against just faking blocks because it's expensive. But that expense makes it vulnerable if someone can afford a 51% attack. Pools add another risk.
Right. POS avoids that specific 51% compute attack, but introduces risks around state concentration, maybe pool collusion, and potential shard attacks if using sharding.
POA and Hashgraph get high security marks in some sources.
But often by being less decentralized, especially POA. And BFT systems need that high percentage of honest nodes to be truly secure. The mechanism directly impacts the security profile.
That energy efficiency. The contrast is just stark. PoJB's puzzle solving is the energy drain.
Absolutely. PoS, DPoS, PoA, PoV, Hashgraph, they all fundamentally change how validation happens, tying it to stake or identity or voting, not just raw computation. And boom, energy use plummets. That chart in one source really showed it. Green PoS tries to make the work itself less wasteful.
Scalability next. PoW's one block at a time nature limits at low scalability.
Whereas PoS, DPoS, PoS, Hashgraph often aim for high scalability, using mechanisms like sharding or faster validation rounds to handle more transactions in parallel. PoV is medium. It's all about how many transactions the system can agree on and how fast.
And finally, decentralization. This feels like the fuzziest one, where the biggest arguments happen.
Definitely. PoW and Hashgraph often get listed as highly decentralized, although PoW has the mining pool issue in practice. PoUS and DPoS are usually seen as medium because stake or voting power inevitably concentrates influence. PoA is explicitly low or centralized.
And that Reddit discussion added crucial real-world context, didn't it? Saying theoretical decentralization isn't the whole story. What about the cost to run a node? Do people actually run them or just trust others? What about the influence of big foundations? They mentioned Radix and Nano as examples in that context.
Yeah, the practical reality can be quite different from the white paper ideal.
It's not just the algorithm, it's the ecosystem around it.
Exactly. And the sources touched on other related things too, latency and finality, which we discussed. How fast is confirmation, and is it final, or probably final?
And that IoT compatibility point. PoA variants in PoS seem better suited for small, low-power devices than energy-hungry PoW.
And we saw mentions of other related tech, like DAGs being used by Caspa as well as Hashgraph, or different design goals like atomic composability that Radix is aiming for, thinking about how transactions interact.
So, given this whole complex picture, trade-offs everywhere, people searching for better ways, one of your sources went deep on a specific research idea, Reticulum, a two-layer sharding protocol. Feels like a good example of that cutting-edge research trying to push boundaries.
It is. Reticulum tackles scalability and security using, 2 layers and 2 phases for consensus. You have process shards doing most of the transaction work and control shards that oversee them.
So nodes are in those types of shard.
A node belongs to one process shard and one control shard that governs its process shard, and memberships are fixed, which simplifies some things.
Okay, process shards handle transactions, control shards manage. How does consensus work then?
It's a 2-phase thing. Phase 1, within a process shard, nodes try to reach unanimous agreement really quickly on whether to accept a proposed block.
Unanimous. That sounds tough. What if they don't all agree?
That kicks it to phase 2. The control shard acts like a referee, or a lifeline, as the paper calls it. It resolves the dispute and makes the final call, usually by majority vote within the control shard. The whole design aims to adjust speed based on attacks and resist attempts to stall the network while always maintaining safety, making sure bad transactions never get finalized.
And the paper mentions specific security things, like preventing nodes being in multiple shards.
Yeah, through a careful bootstrapping process. And safety comes from that rule. A block is only final if it gets unanimous agreement in phase 1 or majority agreement from the control shard in phase 2. If it's rejected, it just doesn't get added. Doesn't affect future blocks.
Did they mention performance?
They did. Experiments showed it outperformed a baseline sharding protocol, Rapid Chain, in things like storage use and download bandwidth. They also analyzed the communication costs, like how much chatter is needed for the voting in the control shards, which uses something called Byzantine broadcast and scales with the square of the number of nodes in the control shard.
And they compared it to another sharding system, Gearbox.
Right. They pointed out Reticulum uses multiple control shards, not just one central control chain like Gearbox, which they argue avoids potential problems like shards overlapping weirdly or needing complex, expensive reshuffling of nodes between shards.
So it's really about iterating, trying different ways to structure sharding to get better results.
Exactly. It shows the kind of detailed thinking going into solving these core problems.
Okay, stepping back from the specific research, the big picture from all these sources seems crystal clear. There's no silver bullet, no single best consensus algorithm.
Absolutely not. Choosing one is always about deciding what you value most. What balance are you aiming for between decentralization, security, and speed?
And it's definitely not a finished story. The sources show constant evolution tweets like GreenPoW, new ideas like PoW, complex new architectures like Reticulum. The whole field is moving incredibly fast.
That Reddit thread really grounded it too, reminding us the trilemma is hard, maybe impossible to truly solve, and that what really matters is how these things perform in the real world, especially with complex stuff like smart contracts, not just theoretical transactions per second.
Yeah, and I thought that comment on Reddit about wanting more neutral initiatives from authentic cryptographers was quite telling. Projects focus purely on building the best tech, maybe without the baggage of big initial coin allocations or dev funds that might skew incentives.
It highlights that this isn't just code, it's intertwined with economics and human motivations too.
So let's wrap up this deep dive. We've journeyed through your sources to get a handle on blockchain consensus, this core challenge of decentralized agreement. We've compared a bunch of algorithms, PoW, PoS, DPoS, PoA, PoH, PoV, Hashgraph, looking at how their designs lead to different strengths and weaknesses across security, energy, scalability, and decentralization, really highlighting that trilemma trade-off.
hmm
And we even peeked at advanced research like reticulum sharding as an example of where things might be heading.
And the takeaway is clear. Each approach forces difficult choices. There's no free lunch.
Definitely. And the field is buzzing with new ideas. Understanding these different consensus models, well, it feels essential if you want to make sense of why different blockchains behave differently and where this whole technology might go next.
It's a fascinating, complex puzzle. Lots of smart people working on it.
So here's a final thought to leave you with. Given these fundamental trade-offs, this constant searching, what characteristics do you think are truly the most critical for blockchain to really break through, achieve widespread adoption, maybe change how things work? And why is it just so darn hard to get all those characteristics, security, speed, decentralization, perfectly optimized all at the same time?